I think I can begin now. Can you hear my voice?
Yes, sir, you are audible.
I lost the momentarily. Okay. So in last class we were discussing these questions. So I think Ripinder is the only one from last class. Ripinder, did you try these questions?
Yes, sir, actually, I've tried in rough notebook, but it is at my home, and currently I'm traveling back to home from college.
Okay, okay. No issues. So we'll try to solve these questions today first, and then we'll go to assignment 6, because assignment 6 is it has only 3-4 questions, so it's very straightforward. All right. So question first is we have to size the vertical tail uh, for the given configuration. There are two pictures where first picture gives you the side view of the airplane and different lengths, and picture 2 gives you the wing planeform area um, for the given airplane. The question is asked, we have to find the weathercock stability, which is directional stability, C and beta, and it should have a certain value. And directional stability is provided by the vertical tail. So effectively, the question to design the vertical tail. Now, by designing vertical tail, we mean we have to find the dimensions of it. So in one of the lectures, go to in one of the lectures we discussed about how C and beta is defined. So C and beta is usually defined as some eta tail volume ratio VV CL alpha of that particular aerodynamic surface. Then we had this 1 plus d sigma over d beta. Okay, so I want to go to everyone and make sure that they understand the notations here we are using. So Akhileshwar, do you understand the notations we are using in this problem?
Sir, only eta, which efficiency is eta, I don't know.
Okay, eta is dynamic pressure at the tail divided by dynamic pressure at the wing, and this number lies between 0.8 to 1.2. All right, and VV is the vertical tail volume ratio, which is,
Yes, sir.
yeah, so the definition is LV divided by S over B, where if you look at the uh, side view of the airplane, so I'll show you the side view. If you look at the side view of the airplane, then from this point to where the aerodynamic center of the vertical tail lies. So this distance. It's not part of it, only this distance. So this distance is LV. And what is SV? SV is this area.
Surface area of the vertical wing.
Yeah, this is the SV. LV, SV. And what is S? S is this entire area of wing. This is only one wing, so the total area will be double of this wing area. Now we go back to that. Yeah.
So sigma.
The other number is CL alpha. I think everyone is aware of CL alpha. Is there anyone who is not aware of CL alpha? I hope everyone is, right? We use it often. So CL alpha is basically the lift slope. I
Lift
can
or
simply
slope.
call it. Yeah. DCL over
D
D
alpha.
alpha. Yeah. So this, let's say we are looking vertical tail from the top. So flow is coming like this. There will be some angle of attack, right? Alpha. And there will be a force generated on it because of this angle of attack exists. So the larger the angle of attack, the larger the CL. The CL is basically CL alpha times alpha. So larger the force when larger the CL. That's how it's connected. D sigma over D beta is the influence because of the side wash. And the idea of side wash is explained in one of the pictures. Probably show from week 4. So week 4. This is the idea of side wash. So what is happening here is that the flow is coming, right? Flying ahead, the flow is coming to the this vertical tail. Now, because the flow interacts with the wing, so the angle of attack will be modified. It won't be the beta. Right now, if there is no wing, the tail will experience an angle of attack beta. But because the wings exist, and there exist these vortices at the wingtips, so these vortices modify the nature of the flow. And effectively, what happens is the angle of attack at the tail changes, right? So the term is here. So sigma is that angle, and the rate of change of that angle with respect to the side slip angle, that is kind of an angle of attack. So that's how CN beta is defined. I think everyone is clear about the terms here. Now the question is, let's write it more clearly in terms of things that we have seen so far. VV is nothing but LV SV over S times B, and CL alpha 1 plus D sigma over D beta. In the question, if I show you again, in the question, CN beta is given to us. Okay, we have to ensure that this much CN beta this airplane has. We have to ensure that. So CN beta is given us as 0.1. Neta, eta is not given. This is not neta, it's eta. Eta is not given to us. So usually we can assume it to be 0.9, 0.95, or maybe 1, but let's assume it's 90%. Right? We're losing some dynamic pressure because of the wing interaction. Then how about LV? This length we have to choose. So I'll go back to geometry and we'll start thinking about what should be the LV. I'm asking for suggestions from you people, because what should be the length of LV? Anyone has any suggestions for us?
Pardon, sir. What's the question?
The question is, do you have any suggestions on how do we choose the length LV? Because clearly the question does not give us any indication about uh, the geometry, how it has been fitted with the fuselage, the geometry of the this vertical tail. So we have to make certain assumptions ourselves, and they must be reasonable. So this exercise is when you work as a designer, not many things are given to you. You have to, from your previous knowledge or from books that you read an article that someone suggested, okay, this much length is in terms of, let's say, percentages of the overall fuselage length. Like someone suggested you something, but we don't have any suggestions right now. So how do we decide length LV?
Sir, we can assume LV as half of the fuselage length.
Half of the fuselage length. Okay, let's see how much that turns out. So this is 1/4, and this is half again, right? So CG somewhere around here, LF by 4. So this is another LF by 4. This should be another LF by 4, and that should be another LF by 4. So clearly, if I consider CG to be at the center of this fuselage, we can work with that assumption. And this length is LF by 4. If I add another LF by 4 to it, then we are at the end. So we have to be within this, right?
Yes, sir, a little bit less than half the fuselage length.
Yeah. So you can also say like a little bit more than LF by 4. So,
Yes.
so plus some number. Now that number could be, let's say this is LF by 4, the whole length. So you can divide it by 2. So you can say LF by 8. That should work, right?
Yes, sir.
Is everyone clear about how do we decided on LV? We're just saying that it's this is LF by 4, and we say that the remaining part is also LF by 4. We just make it half. It should be at the center somewhere. That's how we have decided on LF by 4 plus LF by 8, and that is over LV. Now, what is LV? Sorry, the LF. LF is given to us as 13.7. We can find out what is the length for LV, right? We'll do that shortly. And you can do with your own calculator, because we in this session we want to compute the numbers and have a feel for them. Because you see, the formulas are everywhere. You can just Google any book, research papers. The formulas are there, okay? But the real feel comes when you solve the problem and get a feel for the numbers. How they not to.
Yes, sir, I have
So I
calculated the
suggest
value,
that.
sir.
Yeah. So how much is that length? LV.
5.1375.
L. Wait. Yeah. LV is
5.1375.
1375. All right. So we can cross check it. 13.7, right? So what we'll do is 13.7. It should be divided by 4. Then we add another 13.7. divided by 8. Yeah, 5.1375. That is the number. We have come to that number, and number is 5.1375. That is LV. SV is unknown to us, so we'll keep it as unknown, or rather I'll do is I'll write it a little bit more neatly. That would be better. 90% efficiency. LV is chosen as 5.1375 times SV times CL alpha. So what is the number that we take for CL alpha? Any suggestions from your aerodynamics courses? The only hint we have is that this vertical tail is a symmetric airfoil. It has a symmetric airfoil. Now, what should be CL alpha for a symmetric airfoil theoretically?
C and not will be 0.
Rupinder, your voice is breaking. Actually, we can't hear you. Akhileshwar, you have any suggestions? What should be the theoretical value for CL alpha?
So
When
is
you
it
have a
2
symmetric
pi, I think?
Yeah, absolutely. 2 pi
2 pi.
is the theoretical value, right? Yeah.
Yes,
But the
sir.
thing is, it is a finite wing. But it is a finite wing, right? Let's say, but it's a finite wing. Let's say on both sides you have a symmetric airfoil, but it has a finite length. Now, because of the finite length, the CL alpha will not have that theoretical value. Not just because of it being finite, there are other effects that are also at play. So, how do we modify CL alpha? By what factor it should be reduced such that it is more realistic for an airfoil? For Om, you have any suggestions? Let's say you know the theoretical value of CL alpha for an airfoil. Question is, you have a finite wing. So how do you modify that CL alpha to be used? Rupinder, you have any suggestion?
By dividing it by the number of like aerofoils used, maybe like per radian, this much it should be.
Have you any one of you studied aerodynamics? Someone has answered in the chat. Underground management. All right, no problem. Okay, so the thing is, I also don't recall exactly the number, how it should be modified. But then, since I am sitting on my computer, I can just go and look in the book. So I'll look in the book in front of you because I don't remember. So that's how we should be able to work. Like, you should remember things are somewhere and you know them. You might remember, but as a designer, you can go back and always check. So I have studied these things in some book. I'm going back to get. So yeah, that's here. So this is the CL alpha for a theoretical airfoil. It's 2D. Now, how it should be modified for being 3D, right? So we have CL alpha over pi aspect ratio. All right, so we'll take this formula and we'll modify the theoretical 2 pi into some reasonable values. All right. So the formula was for a finite wing. Remember, for finite wing, you write a capital L, and for theoretical airfoil, you write small l. Just a difference maker.
So the capital L is for a finite wing.
Yeah.
Okay.
AR means aspect ratio. Okay, so this is the formula. Now, you can obviously ask, where does this come from? Nobody, like God has not given you this. So someone has derived it. So the answer is that you can go and study aerodynamics book, Anderson. Somewhere in chapter on finite wings, he discusses where does it come from. So it comes from the actual theory, actual mathematical derivations. It's not just a approximation. Of course, it's an approximation, but it comes out of proper mathematical formulation and derivation, right? So let me explain what are the numbers here. So it's a 2D airfoil slope, lift curve slope, and the efficiency factor is what happens is, how does your finite wing looks like? Let's say if you look from the top, if it's rectangular, it could be tapered rectangular. It could be tapered like this, right? It's the plane form. It's called plan form area of the wing. It's normal rectangular. It's could be delta wing, just like this, right? So there are tons of possibilities for it, and for every one of these shapes, you'll have efficiency factor E. Okay, and efficiency factor E is exactly equal to 1 for which kind of finite wing shape, finite wing plane form area. Anyone has any answer? What kind of plan form area, when you look from the top, will have efficiency factor 1?
In elliptical wing, sir.
Yeah, absolutely. So let me make an ellipse here. If you look at the wing from the top, and if it looks like this, you have a efficiency factor of 1, right? Now, there used to be airplanes in during World War II, and they had a plan form area like this. But these days you don't find this. And the probable reason is, of course, they are aerodynamically efficient, but they are hard to build, hard to construct. May not the stresses and the loadings that usual airplanes experience. So people usually go for the tapered wing, this kind of shape most often. Fighters go for delta for some reasons. The shock waves are formed, and for all those reasons. These are not very popular type of plane areas, right? So it's just a side information. So we'll say that our wing is sort of tapered, and it's very close to elliptical. Like it's not exactly elliptical at all, but we can say that, okay, saying the wing is performing aerodynamically at its best, and it's 1. So keeping all the side information in mind, we go ahead and compute this number. So this is pi. How about aspect ratio? Now we are looking at a vertical tail. Remember? What was the question? Yeah. Our ultimate aim is to find the geometry for this vertical tail. So how should it look like, right? So that is the main aim. Like, what are the parameters I'm looking for here? I'm looking for, it's called the root code. It's called the tip code, CT. It's called the height. Let's say this is the height of the vertical tail. I'm looking for all of these parameters because when you construct this airplane, you need these numbers. Now, the area we can find out from that formula, I'll show you that you can find out the area of this, but you also need these numbers, right? And you also need where is the aerodynamic center located from this line, let's say, or let's say from this line, because the geometry starts here. And if you have certain length, then you can find out at what height it is from the uh, center of gravity. So this moment arm, it will give which kind of moments because of the vertical tail? There are three moments: roll moment, pitch moment, and yaw moment. So what kind of moment this particular length will
Yaw.
give?
Yaw moment.
Yaw moment. Anyone else?
The vertical tail will give the yaw moment.
Vertical tail will give the yaw moment. That is absolutely correct. But that is with respect to the length LV. If you look at it, yeah. When you multiply
Yes.
that side force that it is experiencing, and with respect to LV, it will give the yaw moment. But I'm asking, when you look at it from the side view, not from the top view. If you look at it from the top view, then definitely LV multiplied that side force gives the yaw. Do you understand the difference in two questions? Can anyone answer like which moment it will give? It will give the roll moment. Can you explain like any one of your Kileshwar and Om?
I have no idea about this.
No idea about this. Om, you have any idea why this length? Not LV, but this particular length, aerodynamic center, the vertical distance of the aerodynamic center, vertical tail from CG, and that will provide you roll moment. I'll show you
No,
how it
sir.
will.
Can't recollect.
All right, all right. So let me go back. Erase polling. All right. Wait a minute. I just want to erase everything first. Yeah. So the side force will be like this, right? And this side force is at a certain height from this point. So you can take an axis like this axis, and this axis passes through CG, and it's along the fuselage center line. Now, this distance multiplied this force, it'll give a moment like this now. And that moment is actually the roll moment. Can you reckon that?
Yes, sir.
No?
Yes, sir.
Yeah. And to make things more clearer, I'll go back to another slide where we have shown yeah. See, I'm spending my time on these things because I just want that you must have an overall look on the aircraft, not just the solving the questions that are given to you. I mean, that's sort of very bookish, and anyone can read books. But we want to have a thorough discussion that we understand what we're doing here. Now, when you look at this same force, but from a distance here. So this, with respect to LV, this force will give you definitely the yaw moment like this. But this force is also at a distance from center of gravity, right? In vertical direction, not just in the x-axis. It is at a distance in x-axis, but the distance is also in y-axis, or y-axis. It has a zero distance because this is y-axis, and the force is parallel to y-axis probably if beta is very small. But it has a distance in z-axis also, right? So
Yes.
I'll go back to that slide and show you what I meant. Yeah. Now you understand what I meant. The force is acting here, but this force distance, not just LV. LV is this distance. It'll give the yaw, definitely the yaw. This force will try to rotate their airplane like this. But this distance will try to rotate the airplane which way? Like this. Okay. So, and if you want to understand it mathematically, here is the explanation. The moment is r vector multiplied the force vector. Now this r vector has three components. R is in x direction, xi cap, yj cap, plus zk cap, right? Cross. Force has also three components, right? But for the simplicity, assume that the force only exists in y-axis because the force is in y-axis. Now this Fy will be multiplied with x also, right? With y also, with z also, right? The cross product will happen with all three components of it, x, y, and z. So one force can give you moments about multiple axes, non-zero moment about multiple axes. So that was the idea. Why we have. So the point is, the thing I want to enforce is in your mind, this vertical rudder, the vertical tail, which you're designing, it not only affects the uh, motion in yaw, it also affects the motion in roll, and that is the magnitude. So it's non-zero, but it is small. Wait a minute, I'm getting a call. I might have to take it. All right. So the point is, when we design these surfaces, we have to be very cautious about what are the other lengths, what are the implications of the design we are choosing. All right. So you must understand how much is this distance, this vertical distance of this aerodynamic center. All right. Now we go back to the computation we were performing. Yeah. So this was the computation we had to perform. We took a side track to explain certain things. So this is a CL alpha for a finite wing. So the question was, what should be the aspect ratio? And to everybody's clarity, aspect ratios are defined like this. Let's say you have a certain shape. Let's say okay. So let's say it's fuselage reference line, and it has a certain length. Let's say b by 2, and it has some surface area s, and let's call it p. So aspect ratio is usually defined as the span squared over s. That's how you define the aspect ratio for any geometry. And for a rectangular geometry, let's say it has a length L and height some h. So its area will be L times h, right? So area S. So looking at the formula for aspect ratio, you will have b square, which is length. So L square divided by S is L times h. So L over h. For a rectangular geometry, aspect ratio is nothing but the ratio of length to height for a rectangle. But the geometries in case of aircraft wings, it's not always rectangular. It's something like this, right? So for these geometries, this formula is useful. You have a length, you square it, and you divide it with area. So it's still the ratio. The dimensions are equal, like meter square or meter square. Dimensions are cancelled. So this is aspect ratio. It gives you a sense of the ratio between the length and the width. You can understand it from the example of a rectangular. So if you have a larger aspect ratio, which means the length component is very large. So you will sometimes hear that there are planes having aspect ratio of, let's say, 10, some planes having aspect ratio 15. So you call them high aspect ratio wings, and you will find out that their wings are very long, like they have very large wings with respect to the dimensions of the fuselage. So this is kind of a fuselage, and their wings are very large, especially for the planes that fly at very high altitude. They have a very large aspect ratio. Okay, so that is the feeling about aspect ratio. Question is, what should be the aspect ratio for the vertical tail we are designing? So this aspect ratio could be maybe about 1.5. So the length and the width. So the length is 1.5 times, approximately 1.5 times of the uh, width when we have a perfectly rectangular wing. Okay, so we can go with this number. Now you can ask, why did I get this number? I got this number from a aircraft design book. And where did they get this number from? They got it from experience. They build airplanes and they came to a conclusion, okay, this kind of aspect ratio is good enough for us. So this kind of exercise is helping us enforce the numbers that we should choose. So for a vertical tail and for a horizontal tail, for both of these tails, you can take a aspect ratio about 1.5, and it works. It works good for us. And for the design of a wing, aspect ratio has to be very large. So you should also understand that designing horizontal tail and vertical tail is actually designing a smaller wing. Okay, a smaller wing. So a vertical tail is a wing which is vertically mounted. Horizontal tail is also a wing horizontally mounted. Okay, so an aspect ratio for the wings of the aircraft, it's taken approximately 10. Like 10 is a good number. It's large number. It's fairly good. And taking aspect ratio large has other advantages like reduced induced drag. If you have a small aspect ratio, you will have a large induced drag. So that's another fact. But this is some feeling about aspect ratio that I'm giving you. 1.5 is a good number that we can take in our case. So we go back to the computation and we put this number there. Right. So where we were here. Okay. We have SV, the surface area of the vertical tail. Now CL alpha, this number will come from here. We'll compute all of these numbers first. So SV is unknown to us. And we can, for the time being, we can ignore this number completely because it will be something, let's say 2% in 1. So not a very big change maker. So we can drop this 2 and we can keep it as 1. And how about S times B? So we'll find out these numbers from the geometry that is given to us. Because wing has been designed. So also remember the sequence. First, you design the wing, you design the geometry of the fuselage, and then you come to the design of vertical and horizontal tail. Because vertical and horizontal tail are stabilizers, right? So stabilizers are required at the last when you have sufficient lift forces, right? So in the design sequence, you will always find that these vertical tails and horizontal tails are designed at the last. So this number SB will be available to you when you are at a stage when you design this vertical tail. Okay, so how do we find out these numbers? From here. So quickly give me the area and B, S and B for this wing. And this is one part of the wing. The other part is just the copy of this. So keep in mind that to compute the span, you have to consider the entire aircraft. So give me the numbers S and B for this aircraft quickly. You can take your calculators and try to compute it, or probably help me understand if you don't have calculators right now. So how would I go about S and B? How do I compute from these numbers that are given on this
Sir,
page? Yeah.
for S, we can divide the wing into one rectangular and one triangular part.
Okay.
And the rectangle have a length of 5.2 meter and breadth of 1.34 meter.
All right. So you mean to say this, is it?
Yes, sir.
Okay. So this is the triangle.
Sir, we may use the area of trapezium formula also.
Yeah, that's better actually. And what is that formula?
It is, I think, half into sum of parallel sides multiplied by the distance between them.
Exactly. So
Yeah,
both ans- both answers are correct.
Yeah.
So I'm going with the easy option. So sum of the parallel side multiplied the distance between them. And what is that?
And since uh, distance will be, I think, 5.2 meter here. And
Yeah.
this half will get removed because we are doubling it.
Exactly. Because this is one part of the wing. So there are two parts of the wing.
Yes.
So ultimately we end up with this number. So what is this number? Anyone has computed it? Yeah.
20.
Ripinder, your voice is breaking. You can type if you want, whatever you are saying. And I want others to compute this number S, so we can write it down here.
So I think 21.268.
21.26.
All right. So I'll write it down. 21.27.
27.
Okay. And what will be the B? Yeah. B is also given a number. Yeah. That's right. Everybody understood the idea that you have to double it because there are two parts of the wing. All righty. So we move ahead. We go back to the computation we were doing. And someone please also compute this number, CL alpha number, because we want to have actual numbers in this uh, formulation that we are doing here. Someone also compute this number. We have already decided upon aspect ratio, and we have discussed its significance and what it indicates. Okay, take aspect ratio
Sir,
as, yeah.
CL alpha is coming out as 0.862.
All right, so CL alpha is coming out to be 0.862 per radian, right?
Yes, sir.
Yeah, because 2 pi is in per radian.
Sir,
All right, yeah.
can you please explain me how you taken the aspect ratio of the vertical tail as 1.5?
So I don't have a direct answer to that. Okay, the answer is that I went to a design book and I looked for what is a reasonable aspect ratio for this. Now, one logic could be this, and I'll explain to you what is that logic. One logic is that you don't want to overload it. Let me go back to the picture here. Yeah. So the idea is you don't want it to be, let's say, something like this. When you have a length component is higher and the width component is smaller, right? You don't want something like this because structurally it will induce larger moments here. Imagine its aerodynamic center will be here, right? If you are in, let's say, some crazy beta, some crazy side slip, let's say 10 degrees, 12 degrees of side slip you have, then there will be a large amount of force acting on it. And that force will generate bending moments on this surface and it might break it. So there is a possibility. So what you want is you want to minimize this impact. So for that reason, the tendency is that the length will always be larger than the width of the wing. That is the tendency. Like how large you can take it, maybe 1.5 times of the width. So that is the argument. So it's not a perfect argument, but it works. Okay. Yeah. So all right. So we had quite a lot of numbers here. I'll summarize. Yeah. So we have almost everything here. The only unknown is SV. So please give me the SV. I will wait for everybody. Give me the SV. You know every number here. So CN beta is 0.1. You can write down if you have a notebook. Efficiency is 0.9. LV, we have taken this number. SV is unknown. As we already found, it was 21 something. B already found from that picture. CL alpha, we already found somewhere here. I wrote it 0.862. The last number we have ignored it because we say it's not that impactful right now. Okay, so give me the SV, and then from SV we'll go on to design the actual geometry of vertical tail. So go ahead, do the calculation fast. And if anyone has, so this is the geometry of the wing. I'll probably put everything here. And you can find out the rest. I've given the ideas about everything. All right, we have waited enough. You can find it out, but I'll move on, assuming that we know SV because it's just algebra. You can do that. Assuming that, I'll move on and try to explain to you how to find the geometry. Okay. Now we know that it's going to be a trapezoid, right? The geometry is going to be a trapezoid. You can keep it vertical, probably, yeah. This number is called root chord. This number is called tip chord, this length, and this length is height. Okay, we have to find all of them, and we also have to find the location of the aerodynamic center. At this point, the entire force will act. All right. What we have at hand is SV. We found out that. So just to remind everybody what we are doing here, we are said that the aircraft should have a certain stability properties in directional case. We were given a number C and beta. So that is the desire that the airplane should have a certain stability. Okay, that was the specification. From that specification, we found out how much area we should take for the vertical tail. Once you have the area, now during the computation of this area, we took an assumption that aspect ratio of that wing is 1.5. Taking that aspect ratio again, let's say, how do you define aspect ratio? You define aspect ratio as span. So in this case, it will be height square divided by the area. And we can find out height from here. What will be the height? Right? Everyone agrees?
Yes, sir.
Yeah. You find the height of this wing. I'm calling it wing because it's a small wing. Now, how do we find the CT and CR? Now there is something called taper ratio because it's a tapered wing. The root chord is larger, it has to, and the tip chord is smaller. There is a number called taper ratio, which is defined as tip chord divided by root chord. And in this case, a reasonable number would be 0.5. Okay. This CT should be half of what CR is. Now that relation is given to you. Now find out what are CT and CR. So that is your assignment. Sit down and quickly find out what should be CR and CT. What should be the formula for that? And another number is to you, lambda. So find out in terms of lambda and the other information that you have. Let's say height. You have height. So what should be the value of CR? It's a simple geometry calculation. I want you to do it. I can tell you, but I want that you run your mind and find out the answer. Assume that height is known to you. Height is known to you, aspect ratio is known to you, lambda is known to you, area SV is known to you. What are the unknowns? CR and CT.
We can do it by simultaneous equation.
Yeah, please tell me what is the answer for CR.
So we have the ratio, and we can use the SV equation, area equal to the same trapezium formula, in which CR and CT will be included, and then by solving the both equations, we can get that.
So what will be CR in terms of SV height lambda? Expression for that, because once you establish that expression, it'll remain in your mind, so you can just do it quickly.
Okay. So CR is 2 SV by 1 plus lambda into H.
Good. Yeah, I hope everyone got it. The idea is very simple. You write the expression for SV in terms of the known things or unknown things. Use this ratio to eliminate CT, and then you have this AR, that is a known in terms of all other variables. So you'll get this. I won't write it because it was your task. All right. So once you know CR, you definitely know CT. CT is nothing but lambda times CR. So you have all the numbers for the geometry of this vertical tail. You designed it completely. Now let's go. Let's revise the things what we have done. We have made two assumptions, two fundamental assumptions here. One on aspect ratio and one on taper ratio. I've given it as 1.5. I've given it as 0.5. They may not be perfect. May not be perfect because we just chose them, right? So what do you do when you don't have perfect numbers? What can you do? Any suggestion as a designer? What would you do? Let's say these numbers worked for someone, okay, but they may not work for you for the kind of airplane you're making. Then what is the next step to find out perfect numbers for AR and lambda? Because once you know AR, aspect ratio and lambda, you have all the numbers, all other numbers. You can establish that stability requirement guaranteed. But you had to make two assumptions on AR and lambda. They are not given to you. So what should be the logical next step in optimizing aspect ratio and lambda?
From previous, we can see like what type of taper ratio or aspect ratio used in previous aircraft of similar kind.
That is one way. And from that way only these two numbers came, 1.5 and 0.5. But if these numbers are not good for you, sometimes what happens is you may not get the, let's say you may not construct the kind of geometry you are getting. There could be some limitation with the available resource at your hand. So what will you do is you will optimize aspect ratio and lambda as you desire. So what are the factors that impact it? One is the structural aspect. That whatever geometry you have chosen, can you build it? Can you build it cheaply? So maybe cost is a driver. So what you do is you take aspect ratio and lambda as variables, and you run them. Like take aspect ratio from 0.5 to, let's say, 5. You run it. For every aspect ratio, you have a cost function. You find out the value of that cost function. Cost function is in terms of certain constraints that you have on the design, right? So the idea I'm trying to give here is you formulate an optimization problem where the unknowns are aspect ratio and the taper ratio. And you solve that optimization problem, you end up with answers on AR and lambda. So this whole exercise was to give you a sense that in aircraft design, there will be guaranteed there will be many variables that you have to choose. Okay, you don't know their values beforehand. The first approximation is you go back to the books and find out from historical data what are those numbers. Begin with those numbers, then formulate your own optimization problem. Because see, what kind of airplane you are trying to make, that will dictate the optimization cost function. You formulate that cost function, choose these numbers as variables, and then you find out the answer. These kind of exercises help you understand how things are connected. What is the sequence of design? What should be taken as a variable, right? So these kind of exercises help you build that philosophy in your mind. So, all right. Now we can move on to the next question. The next question is, use strip theory to determine the roll control power. Now, it might not be clear to many of you what roll control power is. So I'll write it down for everyone's benefit. Yeah. Remember, this is the wing. We are given the wing. The geometry is already known to us. Someone has designed for us. Our job is to find out what is the control power of this aileron that they've computed. Sometimes what happens is that you've chosen some aileron from somehow, I don't know how, but then you don't know how its impact will be, because whenever you formulate the control laws that will dictate the aileron angle for different kind of maneuvers, they will require that what is the effect of deploying deflecting aileron by certain magnitude, what happens to the airplane motion. So you need that derivative, and that derivative is known as roll control power. That derivative is nothing but roll generates a CL. CL means the roll moment. How much with respect to delta A? This basically means differentiate the roll moment with respect to delta A. Your job is to find out this number using given geometry and some assumption on the wing. In one of the session earlier, we discussed it in length. So I'll just show you what we discussed, and then we start solving this question. So what we discussed there, I'll probably describe it again because many of you were not there. So let's say this is the wing. This is our center line. One of the aileron, the other aileron. What is happening here? When you deploy or deflect this aileron, camber on this part of the wing changes. I'm assuming everybody understand what camber is. Camber changes on this part also because both of the ailerons are deflected. One goes up, one goes down. Okay. So what happens is a certain change in lift is generated whenever you deploy this. Okay. On one part, delta L goes up, and on the other part, delta L goes minus from whatever lift you were generating earlier. And because of this change in lift on these two parts, you will have a certain moment. So let's say the center of this entire force is here at certain length. Call it some length L. What is going to happen is the net moment about x-axis will be L times delta L. What will be next? Please help me. Plus what? Can anyone help me? What is going to be the total roll moment about x-axis because of this change in lift at these two sections, and both of these sections are symmetric. So the center of the force is at length L.
Yes, sir. It will be not plus here, but minus into minus of delta L into L.
So ultimately it will be plus, right?
Yes, yes, sir. Well, it will twice become twice delta L into L twice.
Let's it got the moment. Let's call it L. L. So that will be the moment generated when you have deflected the aileron, and this roll moment is going to that's what the aim was, to generate roll moment by deflecting ailerons differentially, like one goes up, goes down. So on one of the wing, lift goes down, and on one of the wing, lift goes up, and you have a roll. Okay, so mathematically we have to find a relation that you deploy this aileron by some angle, let's say 2 degrees. How much this LM will be generated? How much roll moment will be generated is the question. How do you formulate this problem? We did it earlier. Watch that. And right now, I will just put expressions here. So we came to this conclusion. CL delta A is equal to twice of CL alpha. Alpha, the CL alpha is of the overall wing, some number tau divided by SB. We had to perform some integration CY dy. I'll explain what these numbers are from Y1 to Y2. Okay, let's look at this picture again. Yeah. So what is Y1? Y1 is this length. Y2 is this length. So what is the spread of aileron? The spread of aileron is from Y1 to Y2. So this integration is being performed from Y1 to Y2. What is C? C is the chord length. Now I've taken a rectangular wing, but for a tapered wing, this chord length will change at every Y station. There will be multiple Y stations, right? When you integrate it. So at every Y station, or rather at every other value of Y, there will be a different C. Okay, but for a rectangular wing, you can take it out because it is a constant. This tau is a number that is defined, actually. It's a defined number. I'll explain what this number is. This number is, can anyone recall what this number was? Like, what's the definition of this number? Achyut, can you recall it? How did we define tau?
Sir, tau, sir.
Uh-huh. Okay. It was defined as d alpha over d delta aileron. What is happening there? When you changing of attack happens because the code changes and the of attack changes for the same relative velocity earlier. Okay, so this number tau quantifies that. And how do you find number? You find this number by by a ratio. So let's make the geometry again. This is the wing geometry, and so you look at one part of the wing. There is one is control surface. This is control surface, and this is lifting surface. So this number tau is actually found out for different ratio between, let's say you have a, this area is, let's call it A1, let's call it A2. So control surface area divided by the lifting surface area, you have a certain number, and this ratio dictates the number tau. So the number tau is a function of this ratio of control surface area divided by the lifting surface area, and this graph is given like this. So I just want to spend a little time on this to explain to you. Let's say your control surface area is 20% of the lifting surface area, then the value of tau is somewhere around 0.4. Okay, so that's how you find it. So this is from some historical data. I took it from some book. Okay, so this is control surface area, and it's a lifting surface area, and it's also valid for the elevator. Let's say you are designing horizontal tail, and you will require let's say this is your elevator, this complete length is your elevator, and this is your horizontal tail. So this is lifting surface area, this cross is the lifting surface area, and this region is the control surface area. You take the ratio of these two numbers, you find out it will be somewhere between 0 to 0.7, and corresponding to that you can find out a tau. For our question, we have a defined wing. Can anyone help us find first that ratio and then tau from that graph? So can someone find us that ratio first? Let's call it A1. Let's call the lifting surface area as A2. What will be the A1 over A2? It will dictate the F. So let's not spend too much time on it. You got the idea what this number is. Okay. I go back to this formula. It might happen that certain things are going over your head, but they will make sense to you when you go back and watch the previous lecture. Okay, so this thing we have to find out, and so what should be CL alpha here? For the we are not given CL alpha in the question, and S and B are known to us. Tau is now known to us because the wing geometry and the aileron geometry is also known to us. C, you can form an expression for C because see, that wing was like this. So, and your aileron was like this. Okay. So your first Y is here. That is Y1. And your second Y is somewhere here. Y2. What is C? This entire length is C. And you can clearly see this entire length is changing. Okay. So here is a little small assignment for all of you. Give me the expression of C as a function of Y. I'll make the geometry. It's 90 degree here. And this is aileron. Okay. And you know these lengths. These numbers are fixed for you. Take it some number as y1. Take this number as y2. This is fixed. Let's say take it you can take it basically whatever C you have, So it also has a taper. Okay, your aileron also has a taper because you can't keep it as rectangular when your wing has a taper. So aileron will have a taper. We can define that taper as something like this. Let's say the chord length of this aileron, chord length of the aileron is let's say CA, and chord length of the wing is let's say CW. And you can take it probably 1 by 4. 1 by 4. So CA will be CW divided by 4, 1/4 of that. Okay, the question is this is y-axis in this direction, and this is root chord, this is tip chord CT. Find out an expression. This is y-axis, so let me write it y as a variable. Find out an expression for C of that entire wing, and you know the length of the wing also, so let's call it some number b. It's a geometry problem. I'm asking you to solve it because if you apply your mind to it, you will learn something. So find out C of y. C as a function of y. Give me that expression. And this is not really useful right now, but it is useful somewhere later. Solve this problem. C as a function of y, because we have a taper wing and we have to perform this integration. So if you find out C as a function of y, I'll end the question here, because then this is just integration problem and multiplication problem. All right. So give me the expression for C of y, then we are done for this problem. In terms of CR and CP, or rather you can take lambda. That is more convenient. Lambda is CT divided by CR. So CT you can easily replace by lambda CR. CR is known to you already in that question. I give you 2-3 minutes and please solve it. After 2-3 minutes, I'll try to solve it. If you don't answer, maybe 4 minutes, and then for the last half an hour, we'll solve the assignment problems, assignment 6 problems. All right. So did any answer? Okay, I'll try to help. Let's make a clear geometry here. So let's say our aileron is somewhere here. Then this length is always there, right? It's fixed length. Everyone agrees? Okay. This length is the only variable that is have to add into this city at every y station. So if you can find the expression for this, then we are done. No. So if I take origin here, but the idea is the origin is here. The origin of y is equal to 0 is here, and y is equal to y1 is here, y is equal to y2 is here. So we have to find the expression from here. So what is happening is that this length is decreasing. And what is the equation of a line? So let's call this length some z, this vertical length some z, and this z is going from some number, the number here, to 0 after a certain length b. So can we say that, and this is, let me be more specific, this is CT, and the remaining length is CT, CR times CT, and you can also say CR minus lambda CT, lambda CR, which makes it CR 1 minus lambda. You can find the lambda for the wing. So this initial length in terms of CR is CR1 minus lambda. It goes from CR1 minus lambda to 0 in a length b. So what is the slope of this line? That is the slope of this line, right? Y over x. Now, when you multiply this line being represented as z is equal to m y plus e. So z at height, we have 2 points. One is y is equal to 0 and z is equal to CR 1 minus lambda divided by b. When y is equal to b, z to what? Can anyone answer? So y is equal to b, what is z? Z is this length, this vertical length. Z is equal to, start from here, you go up. So you have 2 points on this line. Z is equal to c. So equal to 0 here, and is equal to this number here, you have C. So C equal to CR1 minus lambda. Just CR minus lambda. When you put this number y is equal to B, what you have is z is 0 is equal to m is no B. C is already known to you. This CR1 minus lambda. So m is also known to you. That's nothing but minus of CR1 minus lambda divided by you have m, you have C, you have an expression for height z. Did everyone understood what I'm trying to talk here, or it's just going over the head? Can anyone give any indication? Akhileshwar
Understand.
and Achyut?
Not much idea I have.
Okay. How about Om? Om, are
Yes,
you
sir.
understanding?
Yes, sir.
And
Still in
Dipinder?
general.
I think it is on. How about Ashita? I think she has joined new. My get over. Okay, so someone did not understand. So for the clarification, I'll do this again. It's a simple geometry problem. It's the straight line, equation of straight line. So imagine the origin. Okay, this is x-axis. Instead of y, I think it's z-axis. Okay, it doesn't matter. It's a variable. We have a line something like this. So we know at x is equal to 0, this line is here. At x equal to some finite length, x equal to b, or over case to 0. So we know that. And this length is CR1 minus lambda. And so the point is, we have to find out the expression for z, this height, right? The expression for z is nothing but the expression of this line, which is mx plus c. Find out m and c. We did that. We just did that by using the 2 points. There are 2 unknowns. You can have 2 equations, right? For 1 point, you put in this equation, you get 1 equation. For the second point, you put the numbers in equation. 2 equations, 2 unknowns, solve for m and c. You have expression for z. Then you know z, and this length already knows us. So the expression for c will be the total c. It will be ct, that is this length. It's constant throughout, plus the z we have just found as a function of y. So that will be the c of y. The total c of y will be ct plus the function z of y. And the function z of y we can solve using the equation for straight line. Does it make sense for everybody now? Okay, let me ask this. Does it not make sense to someone? So for them, I can try it again. Or everyone is. Akhileshwar, is it clear now?
It's now
No?
little bit understanding I'm having.
Okay, fine. Just think about this. This is your origin 0 0, and it's a coordinate frame you're looking at. Forget this length; it's useless. It's a constant number you're adding at every station. Now you just have this equation. Instead, z you can call it y. Your equation will look like y is equal to mx plus c. Now I have given you 2 points on this line. Let's say I give you a point 1, 2, 3, 4, just for example. can you find m and c for me? Of course you can, because all you have to do is put 1, y is equal to 2. So your equation will be 2 equal to m plus c, one equation. Put the second point, equation will be what? Equal to 3, right? 3m plus c and is equal to 4. All you have to do is solve this set. Two equations to unknown, you have m and c. So it gives you this vertical height from this x-axis. So I imagine this is the x-axis that you know the height for every station. You put a certain value of x in this equation, you get a certain value of y. That's all we need. I replace this with z just to avoid the confusion, because y was the original axis, because the limits were in terms of y1 and y2. That's why. Okay, so the
Yes.
axis became clear, right?
So
Sorry.
so in this graph, the value of slope will be actually negative, no?
Of course, negative.
Yes. Okay. Thank you.
Yeah. Okay, so let's solve this example. Consider this y is equal to mx plus c equation of straight line, and points are at 0 we have some positive 5, and at some 1 we have 0. Okay, so it's a similar kind of example. When x is equal to 0, we are at a certain height here. Wait, we're at a certain height here, but for a certain value b, but in this case let's take it 1, the height is 0, absolutely, right? So 1 comma 0. Let's solve this for m and c. Let's do it. I put x is equal to 0, c is unknown, y is equal to 5. So c turns to be 5. Let's take the point. Y is equal to 0 and m, x is 1 plus c is also known to us, which is 5. 3 plus 5, m is equal to what? Minus 5. So equation becomes y is equal to minus 5x 5. So when you put x is equal to 1 here, find out that, okay, you are at 0. Satisfies the original thing. X is equal to 0, answer is 5. Okay, it satisfies. So it's the, you're finding out this height at every station. You need this equation. So in our case, the independent variable was y. So you have something like this, and the idea is that the c comes out as a function of y. So be a ct and then a function of y. Something like, it will be a straight line equation here. Add ct to that, you have the total chord length here, because the geometry was something like this. So if I place my straight line here, then you know this height and add this height at every station. You have the total chord. So C of y is not go back. Yeah, and we have derived this in one. The number is not. I already discussed that you can take a CL alpha for a airfoil, then you convert it into finite wing, taking the aspect ratio. The geometry that we are given ratio, and then find out the finite wing CL alpha. How is that number? You can find out the aileron area and the overall wing area. Divide the both, you have a ratio. That ratio dictates the tau. Okay, something like this. And I had shown you. From that you can find out tau. And S and B are known to us from the integration perform. So when C has a y, it will be y square here. So the integration will give something y cube, right? One of the term will be y cube. Put the limits, and you finally have CL delta A. That was the question. So the remaining question we will do in next session, the last question 2.11, because we don't have time, and we will also comment on the accuracy of the strip theory. So try to find out some approximation that we are making here, and try to puncture the theory. Okay, try to dig a hole inside it and say, okay, there is some approximation and it's not correct. How it's not correct, we'll talk in this here and next session. this question session. Right now, I want to go to the assignment 6 that we have, so that the original purpose of this meeting is fulfilled. Wait. And we go to the solution. Question 1 is, which of the statements are correct? Let's look at A. Airplane loading has higher stall speed. You guys have solved the assignment, so try to help me why A is correct. Airplane with higher wing loading has higher stall speed. So how stall speed is connected to wing loading? Achut, can you tell us?
Yes, sir. Because when we write this formula, sir, Vs is equals to under root of 2 into Ws by rho CL max, sir. There we see that if the wing loading is higher, sir, that means it is directly proportional to Vs, sir.
Right. This is the formula, right? So this is the formula, and this is your W by S. So V stall is proportional to square root of W by S. So it's connected directly. So you increase one, definitely the other one will increase. And with high loading has higher stall speed. Correct. We have checked it. A low wing dihedral contributes to longitudinal stability. And it's not part of the answers, but can you explain to me? A low wing with dihedral contributes to longitudinal stability or some other stability? And how?
Sir, it contributes to longitudinal stability plus the lateral stability also.
How does it contribute to longitudinal stability? If that was true, then the statement B should have been in the answer.
Sir, but
Say.
sir, the previous time we had somewhere I had read it so that this low wing will contribute both to lateral and longitudinal stability, sir.
No. It's not talking about wing. Wing is there. But the focus is on the dihedral. Wing has contribution to longitudinal stability. That's correct. No questions about that. So I think you misunderstood the question. If whatever you say is true, like this low wing has a contribution, low wing dihedral has a contribution to longitudinal as well as lateral, then this statement should have been correct, because one part of the statement which is given to you here is correct. If whatever you are saying, but that's true. The focus here is on dihedral. You can mount the wing anywhere. You may not call it low, high, mid. You call it wing. Wing has an effect on longitudinal stability. That is a fact. But question here is about dihedral. Can anyone else explain to us how dihedral? What does dihedral impact actually, if not longitudinal stability? Because the answer is wrong. So we should
Sir, it
know.
contributes to lateral stability of the aircraft.
How does it do that? Can you explain the mechanism?
Sir, if we apply dihedral to a low wing, then it starts resembling to a high wing configuration, similar. So it starts contributing to lateral part. Because as such, low wing has low lateral stability. Whenever we try to roll it, bank it, it's not stable. A low wing configuration.
But you're just saying the facts, like you're not explaining. My question is, what is the mechanism by which dihedral affects uh, roll stability? Because it does not affect the longitudinal stability uh, that is established. But what is true is that the dihedral on low wing affects roll stability. Can Rupinder, you explain how does it do? What's the mechanism?
Then maybe it connect to that point that there are components of velocity during a roll,
Uh-huh.
and because of the dihedral angle,
Hmm.
if the airplane is banking in, let's say, right direction, then lower
Mhm.
wing will experience some upward force
Hmm.
from down, and the upper going wing will experience a force in down direction.
Not down direction. I mean, there will be a lift, but that lift will be reduced on the wing
Reduce,
that is.
yes, sir.
Uh,
Yes, my point.
Still, I think it's not clear to most of the people, so I'll explain it once more. Right. So idea is it's low-wing, right? So make it like that. This is the dihedral angle from horizon. This angle tau is the dihedral. If there is a roll, okay, if airplane is in roll, what happens is the airplane will develop a side slip beta, and because of a side slip, it experiences a side wind, a wind coming from this direction. So one of the components of this side wind is directly going normal to the wing, and this normal component of the wind to this plane of the wing, it increases the angle of attack on the downgoing wing, and it increases the angle of attack on the wing that is going up. So that change in angle of attack delta alpha is quantified with tau times beta. Beta is the side slip angle, tau is this dihedral. So because there is an increase in angle of attack on the downgoing wing, let's say it's going down here, then you have extra lift on it, right? And you have a loss of lift on it, right? Then what happens? The extra lift will generate a moment about x-axis, the airplane x-axis, and then restore the roll. So that's how it works. In the previous lecture, we have discussed in detail how this is derived. So you have doubts, you can go back to the previous lecture and understand the proper mechanism and how these components are decomposed, and how do we come to the conclusion that the change in angle of attack because the the dihedral exists. Let's take a case where dihedral doesn't exist. Okay, there is no dihedral. You go into roll, you side slip, you have a side wind, but this wind has no components perpendicular to the wing, right? The component of the wind that is perpendicular to the wing is going to increase the angle of attack by definition of uh, of angle of attack. So no change in angle of attack, you have no contribution to roll stability because you don't have a dihedral. So tau is 0 in this case, no roll stability. But in this case, you will have a change in angle of attack, and that's why you have a roll stability. All right, let's go to the next question. Next option. A high wing contributes vector stability and longitudinal stability. Well, how is it wrong? Can anyone explain how is this wrong?
Sir, I just know the fact that high wing is not longitudinally stable as much, but the reason as such I don't know. It's because of the moments that I can recollect.
Okay.
Drag moments.
Aripendra, why high wing is bad for longitudinal stability?
So actually, I also don't know about the longitudinal stability. Maybe it will because the fact that the mass is hanging below the wing. Maybe it could be a factor.
So, so what happens because of that? So is it correct like this part? A high wing contributes to lateral stability. Is it correct? This one?
Yes, sir. So I think C
Yes,
is
sir.
also
It,
absolutely correct. C entire statement correct because longitudinal instability it is written. So
Yeah, I also noticed it now
yes, sir. So the entire statement is correct.
because hiving is contributing to lateral stability. That much is correct, and longitudinal instability.
Yes, sir. So the entire statement is correct. Actually, I guess.
I don't know actually. We might have to rethink about this option. I'll skip it and probably talk about it with the TAs who made these assignments. Okay, I don't know the answer to this. I'm leaving it here. Winglets contribute towards minimization of wingtip vortices and thereby it. So how is it correct when you answer?
yes, sir, they are true, sir, because uh, they will help to reduce the vortex strength at the tip of the wing.
So this
Yeah,
this thing I don't know their mechanism actually. So can you explain how the winglets are minimizing the vortex?
right. So imagine a wing like this. Okay, what is happening is, let's say there are no winglets. There is high pressure acting at the bottom and a low pressure acting from the top. The top surface has higher speeds, so low pressure. Flow will go from high pressure to low pressure like this and like this. So there are vortices being created because of the nature. The flow wants to go like this. Now what you do is you put obstacles into the flow, something like this, right? Now there will be some increase of pressure on these parts and you don't have a easy path to go like this. So it eliminates the vortices, not completely, but to some extent. That's the mechanism.
Okay. Actually
Session.
preventing the lower air to come up.
Yeah, that is the idea. Which of the following
Right.
are true for a
Thank you.
typical flight profile of a rotor? Yeah. So I think this question is coming twice. Anyone thought? Can you confirm? I have seen this question in one of the assignments earlier also, as far as I can remember.
Week 4 it was there.
Yes, sir. It was in earlier assignment.
It was in week 4, I
So you can skip
think.
it. Yeah, we've discussed it. So quadrotor, quadrotor, all of the weight is balanced by the thrust. So even if it is hovering, let's say it's at a certain height and it's hovering there. In hover, uh, thrust is balanced by the weight exactly. But if you do a maneuver, let's say you move in X direction or Y direction, translation motion, you have to tilt your quadrotor. So when you tilt and you want to maintain the height, then okay, let's make the diagram and make it clear to everybody. So let's say this is your quadrotor. This is the quadrotor, and there are four components of the forces they're generating. CG, the weight is acting on the CG downwards. T by 4 is being generated by every rotor. The net is T balances W. But let's say you're moving horizontally. So what you will do is you will tilt your vehicle, let's say like this. So you will tilt your vehicle, and that will be the net thrust. One component, let's say you tilt it by angle phi. So it will be T cos phi and it will be T sine phi. The T sine phi component is giving it the translation motion in one of the direction. And I'm saying that let's say you maintain the height. So you maintain the height, it means you don't lose the vertical force. So T cos phi is going to balance the weight always, right? So what will be T? 1 over 2 W. 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 1 it will be 1 over cos phi. And cos phi is going to be between 0 to 1. So T over W is going to be greater than 1. Got it? So whatever maneuver you do, you have T over W greater than 1 for quadrupole. And for fixed wing aircraft, T over W is less than 1. How do we know that this one?
Because we need to balance drag. Weight is balanced by lift,
That is
and
absolutely
drag is
correct. But
very less.
you're just saying it is very less, but how do you know that? Is the question.
So we know the values of CD.
Uh-huh.
The main dependence is on CD, and
Yeah.
we know that CD is very low value, 0.0 something, always, most of time.
But still, all of your arguments are based on the feeling that the drag might be small, but you have not computed it exactly, whether it is less or high, right? So rather than answering it with feelings, we should try answering with maybe some math. Can anyone help me? What kind of math will help us? So what is the amount of thrust for a typical airplane? Like how do I compute that? Let's say the weight is W, weight of the aircraft. Now give me what is the thrust of that aircraft in steady flight. Assume any number you want to assume
W,
to be on. What will be the
W by L by D.
W by L by D? Very good. Who answered this question? Om.
Me, yeah.
Definitely greater than 1, right?
Yes, sir.
Yeah. So how do you know that? Because you talk about CLCD always. CL over CD. This ratio. One my number. You have talked about it length. So you know this ratio, right? So for typical airplanes, you have a feeling about this number now. And now you see that T over W will be what? It will be 1 over CL over CD. And that number you already know is greater than 1. So T over W is less than 1. That's how you answer it. And how about this question? You have two different aircrafts, a motor glider, a surveillance drone. Power to weight ratio is given, lift to, yeah, we were talking about this number, right? L by D. So it's a large number, 20, 30. Surveillance drone has 10, motor glider has 30. So this number is, we have a feeling for this number. So that's how we can answer. All right. So the question is to find out the rate of climb, and rate of climb has a formula. Excess power divided by weight. Excess power is what? Power which is available to us and power that is required. That is that can give us maximum rate of climb. If we are flying at a power which is equal to the available power, then you can't climb. You can only climb when you have excess power, which means your engine can produce more power, but you require less power, right? If that the difference exists, then only you have a rate of climb. So this formula is derived in some lectures on. I think it derived it now also, but I want to skip it actually because we are already over the time. And if anyone has a doubt, I can answer it in next session. But take it for granted, excess power divided by weight is the rate of climb. So you do some manipulation here. You how much power you require? Thrust into velocity. That is the power that you require. So you substitute thrust into velocity. Then what happens? Thrust is equal to drag when you are in steady flight, and when it is drag, and lift is equal to weight. So you replace PR with drag, W with L. You have this number, and available power is some percentage of the shaft power, right? And that efficiency factor is also given, which is 80% efficiency we have. So now all of the numbers we have available to us, and then we simply compute it and find out the answer for rate of climb. With with increase in wing loading, the corner velocity of the aircraft will increase. Can anyone answer this question? Question 4.
Yes, sir. Same, sir. The V stall formula.
Right. Very good. But to everyone else, the
Also,
corner
sir, during a
velocity is
maneuver,
what?
there is a higher factor, loading factor.
Uh,
And if there is a loading factor, then we will multiply with N in
so
W.
load factor is defined as lift over W. L is basically the vertical force on the aircraft. Okay. So vertical force is what? Half of rho V square S times CL max. You fly at a CL max divided by W. So now what is corner? What is corner velocity actually? Oh, what is happening here?
Sir, I presumed it to be the velocity needed to make a turn.
That is correct actually, because the load factor will be more than one in turning maneuvers. We will discuss it at length in probably the next session. We are already over the time, but I still want to give you some idea. You have seen this something called Venn diagram. So this
Yes, sir, I have
velocity
seen,
is the
sir.
corner velocity. Yeah, this is plus n, this is minus n. So you fly you fly different maneuvers, and in those maneuvers n is always greater than 1. In steady flight n is equal to 1 because lift is equal to weight. It's balanced. So how do you make this part of the graph? To make this part using this formula, n is equal to half of rho v square s cl max. Remember, we have to take cl max always divided by the weight. Now what is happening here is you keep increasing velocity. Okay, your weight is fixed, your surface area is fixed, cl max is fixed. So n is turning out to be proportional to v square. So it's a quadratic here. If you see that, it's a quadratic. What is, you keep increasing the velocity, the vertical force is increasing, and n is increasing, right? At larger velocity. But there is a structural limit aircraft can experience after that load factor, or after a lift, right? Certain amount of lift, that's maximum lift, your structure will break. Like something will break. So that limit is imposed by structure. So that limit you impose, and you basically cut it short, n proportional to v square, or n is equal to some kv square type of parabola. So it's a parabolic curve here. You truncate it here, and that velocity is called the corner velocity. And this corner velocity is directly proportional to the square root of w over f. If you keep k constant, and then you can find like simply find the relationship between v and w by s by simple manipulation. Here you will find out that v is proportional to square root of w by s. That's what the answer said. But we will discuss it about the Venn diagrams and something more. Okay. So right now we can simply say that it increases. And which of the following option is not correct? Velocity at minimum power and velocity at minimum thrust are same. They're different.
Yes, sir, they are different,
They're
sir.
different, right? And lift coefficient, minimum power and minimum thrust conditions are not same. Therefore, velocity at minimum power and velocity at minimum thrust will not be same. So the question is, how do you find the lift coefficient corresponding to minimum power and minimum thrust, both? If you can recall it, I'll just say it. For minimum drag, you have to maximize this, right? And for minimum power, you have to maximize this. and CL corresponding to maximization of this, and this will be different, obviously. We've done these calculations in the beginning part of this course. So definitely answer option 1 is not correct. Others are correct. If you have any doubt, you can ask. I hope you don't have a doubt. At equilibrium, net moment about CG is 0. That is the definition of equilibrium. So correct. Airplane with higher wing loading has higher stall speed. We have already answered this in first question. At aerodynamic center, pitching moment coefficient remains constant irrespective of angle of attack. That is the definition of aerodynamic center. So all three are correct and this is wrong. So this is the answer. We done with the assignment also. So in the next thing, we'll talk about these VN diagrams at some length because it's very important to understand them. And we'll try to solve the remaining question, this question 2.11. And what more, we want to comment on the accuracy of strip theory also. Yeah. So these 2-3 things we'll cover in next session. And that's all from my side today. Thank you for joining, everyone. Now you can leave the meeting.
Sir,
Thank you, sir.
Yeah.
Thank you very much.
sir, can you please give us the link for this recording, sir? Because sir, I'm not finding anywhere, sir.
You alone or no one can find?
Okay,
Can you
sir.
guys confirm?
Sir,
Like I'm asking this
they are
question
being
to everyone.
uploaded on YouTube. They are being uploaded on the YouTube.
So
Can
you
you please
have
tell
those
me the
links
name
or
of
not?
the channel?
I will
Uh,
actually send you the spreadsheet link, just a second. All the videos of both the lectures you will find there.
Yeah. I'm doing same thing. I'm sending. So this is the
This is
chat.
the one.
Yeah.
This is the one.
This is my channel, okay? And I upload on my channel. Tanya uploads on her channel. So the
Yes,
links to
but
both of the
in this,
channels are given.
yes, sir. In this spreadsheet, all the lecture links are there.
Exactly. And also upload that content in Drive, so you can also access that.
Yes,
Like
sir.
Yes,
slides.
sir.
Even
Got
that
it.
is there.
Thank you.
Yeah. So see you in the next session. Bye for now. You can leave the meeting.
Thank you, sir.
Thank you,
Thank
sir.
you, sir. Thank you very much, sir.